Only being here for a couple of weeks. I adjusted probably within a matter of hours. I would imagine the adjustment after this mission will probably be in a matter of weeks.
Hello, my name's Cliff Whitford from John Hanson Middle School.
Rick is Ron Black from John Hanson Middle School.
And I'm Matt Binder, a representative of NEAT. What is the coolest thing about the Educator Year in Space?
It's really good to hear Ron Black's voice and have someone there from John Hanson Middle School and a fellow NEAT teacher. For me, overall, to shine a light on one of the most important jobs there is, and that is being a classroom teacher. To just say thank you to all the amazing people in our nation's classrooms and the classrooms around the world who sacrifice so much with our most precious resource, our children.
Hi, my name is Rebecca. What is your educational career path to becoming an astronaut?
You have to have a degree in science, technology, engineering, or mathematics, something in a STEM field. And then NASA really wants people who have done things, who have been out and done operations. That's what we do. We do things. We don't have a lot of meetings up here. We're up here going from activity to activity to activity. So a degree in science and technology, engineering, mathematics, in one of those fields, and some experience doing science either in a lab or in the field, and having a really broad experience with working with a lot of different people as well.
Hi, my name is Max Young Mason. What information or discoveries that we're close to uncovering are you most excited for?
Well, just outside the space station, and my friend Drew, who just went by, he helped install it. There's a device called the Alpha Magnetic Spectrometer, which is really helping us understand very fundamental questions about the cosmos. And we actually have another experiment that we're trying to get started up here as well, Cold Atom Lab, which will also help us gain better understanding. Those are really fundamental questions. You know, where did we come from? How did we get here? What's the very fabric of space-time? And unraveling the answers to those questions, I'm not smart enough to do it, but there's some really, really bright people working on it, and I look forward to hearing more of those results.
Hi, my name is Morgan. How do you shower in space?
Yeah, my next encounter with running water will be when I land on Earth on October 4th. But we do have access to water. We shower with this. Inside this bag is a towel and some soap. And we actually hook this up to a water dispenser, fill it with warm water, and then we use a wet towel to wipe off with. We also use rinseless shampoo, and then dry off and move on to getting dressed and ready for the day.
Hi, my name is Dylan.
And my name is Morgan, and our question is,
what food do you eat, and does it taste different in space?
We eat similar to what the military eats when they're forward deployed. We have meals ready to eat. So this is like a packet of pesto and pasta with pesto sauce, which I'll warm up. And in this packet here, which looks like a little brick, is actually beef stroganoff, which we'll add water to and warm it up. It tastes the same here as it does on Earth. And that's good, and it's also one of the challenges because it tastes the same, and we eat a lot of the similar stuff. We have a pretty good variety, but Drew and I will be up here for almost 200 days, and you get to sample everything many times, and but it's good and it's healthy.
This is Jesse, and he's wondering if you can see Mars from the International Space Station, and if so, what does it look like?
Yes, you can see Mars. I've seen it from here. I actually saw Saturn the other night. It was really beautiful, a sunrise over the Nile River. And it looks very similar to the way it does on Earth. The distance, Mars is so far away from Earth and so far away from the space station. It is a small red dot, just like it is looking from your backyard. And Saturn from here is very similar too. I was actually using a pair of binoculars to just barely make out the rings. So very similar to the view you have back home.
Thank you so much, Ricky.
Oh, my pleasure. It's wonderful to spend some time with you at Goddard Space Flight Center. I hope you have a wonderful experience at summer camp, and I look forward to catching up with you again when I get back on Earth in October.
Station, this is Houston ACR. That concludes the event.
Thank you to all the participants at Goddard Space Flight Center. ISS will be resuming normal space-to-ground audio.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
What does your body feel like in zero gravity?
What inspires you to become an astronaut?
What exercise do you do? And do you sweat in space?
Would a yo-yo work in microgravity?
So it works.
Station Houston on 2, are you ready for the event? 2, are you ready for the event?
We are ready for the event.
Goddard Space Flight Center, this is Mission Control Houston. Please call the station for a voice check. Please call the station for a voice check.
This is Goddard Space Flight Center. This is Mission Control. Please call. Station, this is Goddard Space Flight Center. Summer education camps. How do you hear me?
We have you loud and clear, and welcome aboard the International Space Station to Goddard Space Flight Center. Good to hear you, Trina.
Good to hear you, Trina. Hi, Ricky. Good to hear you, too. Thank you.
It's great to be here with you.
It's great to be here with you, too.
Hi, my name is Harrison.
And my name's Annalisa.
What do you
see in outer space? Over.
Well, I can actually see you guys, not you specifically, but we spend a lot of time looking back at Earth. We are about the same distance. If you were to drive to Goddard, from Goddard to Ocean City and then back to Goddard, that's about how high we are over Maryland when we fly by, which we did just yesterday. And so we spent a lot of time looking at the Earth. At night, we can see the same planets that you see. We can look at Mercury or Venus, but you can see those from Earth, Mars, Jupiter, and Saturn. The stars, the same ones, but we probably see a few more because we're free above the Earth's atmosphere.
Hi, Ricky. My name is Tashiana. Thanks for answering our questions. I'm wondering, what can we learn from space missions and exploring other planets that might help us in adapting to a changing climate here on Earth?
Tatiana, fantastic question, particularly at Goddard Space Flight Center, which invests so much energy in studying our home planet. Studying other planets helps us understand the mechanics of things that happen here on Earth. And right beside us in our solar system, we have a planet, Venus, which suffered from runaway greenhouse gas and climate change. And Mars, which probably had a thick atmosphere at one point and now really has a very thin one. So Mars, much like on Earth, when we want to understand what happens in past climates, we go to the poles and we drill into the ice and look at what the atmosphere was like. So I think getting understanding of the mechanisms and what happened over time to the atmosphere and other parts of the planet will give us a better understanding of how climate change is and will continue to affect Earth.
Hi, my name is Sinai. What are some long-term health issues from being in space?
I hope not many, but we are up here. We get exposed to a bit more radiation than you do on Earth. our bone structure changes a little bit. We come back with the same bone density because we exercise a lot, but our bones are just a little bit different when we get back to Earth. Some of us will have vision changes, slight vision changes, because our eyes, as they adjust to the way our body changes here on the International Space Station. So that's one of the reasons we're here. If we're serious about going out and exploring the solar system, we need to keep people healthy for the long haul.
Hi, Rick. I'm a distant relative, it says here on my card. We were wondering how you're doing, and I wonder if you'd show us a cool microgravity trick.
I am glad you are at summer camp and that you have some adult supervision. That's good to hear. Well, I'm actually just standing here in a foot restraint, but if I let go of my foot restraint and just give a slight shove, I can float away from you quite easily and then hang upside down and talk to you a bit like a bat.
Hi, my name is Riley. Azaria. Do you have lights and TVs on the International Space Station?
Yes, we need lights up here. We have the sun to, of course, which gives us some light through some of the windows, but we need lights in the places where we don't have windows. Television, we get our programs sent up to us from the ground, so the news is about a day late, and we either watch it on something like this or on a computer. We don't really have a reception television or cable television. The cable would have to be pretty long and growing ever longer. But we do get plenty of TV when we want to watch it.
Hi, this is Lydia, and she wants to know if you have flowers on the International Space Station.
Hey, Lydia, I wish we had more. We've been growing plants up here since 2016, but that is definitely one of the things you miss, the smell of earth, plants and trees, and the taste of fresh fruits and vegetables. But right now, we actually, just back behind where this camera is, there's an experiment I've been working on where we've been growing these small plants to get an idea of how they change up here in microgravity, and they're starting to get some really, really small flowers. And then back on the in the Columbus segment, which is the Columbus module, which is built by our European friends, I was working on an experiment this morning where we're growing algae. When we head out into the solar system, we're going to need to be able to grow our own food and have plants there to provide us oxygen and energy.
Hi, my name is Warren, and I wanted to know, how does it feel when you launch?
It is probably the most exciting ride you could ever have in your life. Think of the coolest roller coaster you've been on, and that the ride lasts 8.5 minutes, and when it's over, you're looking down on this magnificent planet. So it's all those sensations, all wrapped into an 8.5 minute long thrill ride.
Hi, my name is Sophia. When you first got into space, how did your perspective of Earth change?
You want everyone you know to have the same view of this magnificent planet we call home, because you get a feel for how precious it is and how fortunate we are that it's there for us. When you look at the Earth as the sun's setting or when the sun's rising, you can see the atmosphere, and it's just razor thin. And that little bit of atmosphere is all that protects us from the harmful radiation of space and provides us oxygen to breathe. And as thin as it is relative to how big the planet is, there is no way we can pump stuff into that atmosphere without having a cost for our actions.
Part of the Earth looks like nobody's been here. It looks like a desolate planet. In other parts of the Earth, you can definitely tell that we have our footprint. You see smoke coming off of power plants in China,
Goddard, are you still there?
Okay, this is Sophie, and she would like to know why you need to wear helmets in space.
I need one in the space station to keep from bumping my head, but they protect us from temperature changes once we're outside the International Space Station, and it also protects us from the vacuum of space, the lack of air and the lack of air pressure.
So why do we wear helmets in space? So you have two types of helmets. That you get into. It's like that it has communications, water in it, and so that helmet has lights on it for you get a sunrise and sunset every 45 minutes. So that helmet is much different from a spacewalk perspective than for launching anything like an aircraft pilot.
Hi, my name is Christopher. Does the International Space Station have a universal docking infrastructure, or can only Russian-made spacecraft dock there?
Yeah, I flew up on a Russian-made spacecraft, and we docked to one of their docking ports, but we have an IDA, a docking adapter, on our modules for the upcoming commercial crew vehicles, which are going to launch out of the United States. So when the American rockets are ready to go from our commercial partners, and those capsules arrive, they will dock here to the U.S. segment of the International Space Station.
My name is Jaden. My question is, can you use a cell phone in space?
You can use it for taking pictures, maybe listening to some of the music you have stored on there, but we do not get a signal. And I tell you, I miss a lot of things about Earth, but my cell phone is not one of them.
Hi, my name is Vincent, and I was wondering, how do you feel physically and emotionally at launch?
Yeah, you're ready. We were training for a year or so, getting ready for that day. You have a lot ahead of you that you got to come up here and do. It's exciting. It's a little scary, but it's you're ready to go and ready to get on with the mission. It's a very, very exciting day, and it's amazing the way just the emotion and the senses that kind of get frozen in time, and you just can recall those just about at any time. Just remember how exciting a day that is.
Hi, my name is Maxwell, and what does the moon look like up close?
I would like to know that's a journey that someone your age is going to make. Probably not me, but we're not that much closer to the moon than you are. We're only about only a couple hundred miles closer, so it's a little clearer, but it's about the same size, and it really doesn't look much different up here than it would from a really clear sky back on Earth.
Hi, my name is Ben. What does the world look like from space?
It looks like a very peaceful, beautiful place in the black of space, and you don't see any international boundaries. You don't see the kind of the turmoil that can happen. It just looks like a really peaceful oasis out in the solar system. It's a magnificent place.
My name is Ava. How is life on the International Space Station different from life on Earth?
I'm looking at one of my crewmates, and he's one of the big reasons it's different. We're only up here with 6 people, and we get to spend a lot of time together. So that part is fun, but it's also different. And down on Earth, you get to interact with a lot of different people, separated from your family and friends. All in all, it's a really, really exciting experience, and the work up here is really rewarding and fun.
Hi, my name is Otto. After you have been in space for a while, how does your body feel when you come back to Earth?
Well, I only have one data point for that, and I felt really heavy and really dizzy the last time I landed, and I was only up in space for a couple weeks. So I'm kind of anticipating maybe the same thing this time, but I've been up here a lot longer. Back after only being here for a couple weeks, I adjusted probably within a matter of hours. I would imagine the adjustment after this mission will probably be in a matter of weeks.
Hello, my name's Cliff Whitford from John Hanson Middle School.
Rick is Ron Black from John Hanson Middle School.
And I'm Matt Binder, a representative of NEAT. What is the coolest thing about the Educator Year in space?
It's really good to hear Ron Black's voice and have someone there from John Hanson Middle School and a fellow NEAT teacher. For me, overall, to shine a light on one of the most important jobs there is, and that is being a classroom teacher. To just say thank you to all the amazing people in our nation's classrooms and the classrooms around the world who sacrifice so much with our most precious resource, our children.
Hi, my name is Rebecca. What is your educational career path to becoming an astronaut?
You have to have a degree in science, technology, engineering, or mathematics, something in a STEM field. And then NASA really wants people who have done things, who have been out and done operations. That's what we do. We do things. We don't have a lot of meetings up here. We're up here going from activity to activity to activity. So a degree in science and technology, engineering, mathematics, in one of those fields, and some experience doing science either in a lab or in the field, and having a really broad experience with working with a lot of different people as well.
Hi, my name is Max Young Mason. What information or discoveries that we're close to uncovering are you most excited for?
Well, just outside the space station, and my friend Drew, who just went by, he helped install it. There's a device called the Alpha Magnetic Spectrometer, which is really helping us understand very fundamental questions about the cosmos. And we actually have another experiment that we're trying to get started up here as well, Cold Atom Lab, which will also help us gain better understanding. Those are really fundamental questions. You know, where did we come from? How did we get here? What's the very fabric of space-time? And unraveling the answers to those questions, I'm not smart enough to do it, but there's some really, really bright people working on it, and I look forward to hearing more of those results.
Hi, my name is Morgan. How do you shower in space?
Yeah, my next encounter with running water will be when I land on Earth on October 4th. But we do have access to water. We shower with this. Inside this bag is a towel and some soap. And we actually hook this up to a water dispenser, fill it with warm water, and then we use a wet towel to wipe off with. We also use rinseless shampoo, and then dry off and move on to getting dressed and ready for the day.
Hi, my name is Dylan.
And my name is Morgan, and our question is,
what food do you eat, and does it taste different in space?
We eat similar to what the military eats when they're forward deployed. We have meals ready to eat. So this is like a packet of pesto and pasta with pesto sauce, which I'll warm up. And in this packet here, which looks like a little brick, is actually beef stroganoff, which we'll add water to and warm it up. It tastes the same here as it does on Earth. And that's good, and it's also one of the challenges because it tastes the same, and we eat a lot of the similar stuff. We have a pretty good variety, but Drew and I will be up here for almost 200 days, and you get to sample everything many times, and but it's good and it's healthy.
This is Jesse, and he's wondering if you can see Mars from the International Space Station, and if so, what does it look like?
Yes, you can see Mars. I've seen it from here. I actually saw Saturn the other night. It was really beautiful, a sunrise over the Nile River. And it looks very similar to the way it does on Earth. The distance, Mars is so far away from Earth and so far away from the space station. It is a small red dot, just like it is looking from your backyard. And Saturn from here is very similar too. I was actually using a pair of binoculars to just barely make out the rings. So very similar to the view you have back home.
Thank you so much, Ricky.
Oh, my pleasure. It's wonderful to spend some time with you at Goddard Space Flight Center. I hope you have a wonderful experience at summer camp, and I look forward to catching up with you again when I get back on Earth in October.
Station, this is Houston ACR. That concludes the event.
Thank you to all the participants at Goddard Space Flight Center. ISS will be resuming normal space-to-ground audio.
We have been really excited about the NASA challenge. If we actually solve a problem, it would pave the way to engineer large, complex tissues.
We think that we have a solution to a major problem in tissue engineering.
The requirements of this challenge falls directly in line of our ongoing research.
The challenge proposed by NASA and the New Organ Alliance is the same problem we have been trying to solve for the past 5 years.
We are interested in improving our understanding of vascular bed formation.
Taking the device to the International Space Station and observing how the vasculature expands and creates in the zero gravity environment is extremely exciting.
We think it's really exciting to potentially work with the team at NASA and bring our technology into space. That would be wonderful.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
I would now like to hand it over to Dr. France Cordova, Director of the National Science Foundation. Please join me in welcoming Dr. Cordova.
Thank you, Amanda, and good morning, everyone. Welcome to the National Science Foundation, the place where discoveries begin. In 1912, physicist Victor Hess had a problem. He was trying to find the source of a particular kind of ionizing radiation that he believed came from space, but he was just too close to the ground. So Hess did what scientists and engineers have done throughout history. He devised a way to collect the information that he needed. Accompanied by what must have been some very patient friends, he began 2 years' worth of balloon ascents, taking electroscope measurements far above the ground. Just 9 years after the Wright brothers' first flight, in a small basket 5,000 meters in the air during a near total solar eclipse, Victor Hess found the first evidence of cosmic rays. For this discovery, he was awarded the Nobel Prize. As so often happens in science, Hess's findings raised new questions, opening the door to a mystery that has endured for more than a century. What are the origins of high-energy cosmic rays? In 2004, a group of researchers, supported by the National Science Foundation, also had a problem. They wanted to track high-energy neutrinos, elusive subatomic particles that travel the universe at almost the speed of light. High-energy neutrinos are incredibly hard to study. They have no electrical charge and are almost weightless, penetrating matter as they whiz across the cosmos. We can only see evidence of them when one happens to crash into the nucleus of an atom. If you had a detector the size of your body, you might register a collision between a high-energy neutrino and a nucleus in your body only once every 100,000 years. So like Hess, these researchers devised a clever solution. They created a cutting-edge laboratory in Antarctica, one of the harshest environments on the planet, and also the only place suited to this task. They constructed, with NSF funding, the Ice Cube Neutrino Observatory, which sits above a cubic kilometer of clear crystal clear ice that is permeated with over 80 long strings of sensitive equipment, a massive engineering undertaking. You can think of these strings like strings of pearls in which every pearl is a digital optical monitor like the one on this stage. And there are over 5,000 of them in this cubic kilometer of ice. Today, I'm proud to announce that using data gathered by NSF's IceCube, an international coalition of scientists has taken a major step towards solving the high-energy cosmic ray mystery, echoing Hess's spirit of innovation. They believe they may have identified at least one source, another galaxy billions of light years away with an especially active nucleus known as a blazar. Blazars are powered by supermassive black holes and spew immense jets of mass and energy that can be the size of a visible galaxy. These jets accelerate cosmic rays and contain particle collisions that result in high-energy neutrinos. And as in all blazars, one of those jets points directly at us. This discovery will enhance our understanding about how the universe is built and behaves. We will better understand the nature of the universe's immense cosmic accelerators, which are far larger and more powerful than anything we could build on Earth. Despite all the progress we've made with particle accelerators, like the giant ones at CERN and Fermilab, we still can't produce anything with nearly the energy of these cosmic particles. So we have to turn to the heavens to deepen our understanding of the highest energy processes. Creating NSF's IceCube was a difficult process, but the rewards have justified the investment and again demonstrate the importance of building entire ecosystems of basic research. This work would not be possible without the foundational discoveries made by neutrino physics pioneers, including Nobel laureates Melvin Schwartz, Frederick Reines, and Raymond Davis, all NSF supported. Discoveries like this build on advances that result from years of painstaking investigation. The federal government has a unique role in these discoveries as the only supporter with the resources and mission to ensure that high-risk, high-reward, long-term research continues. Like the recent detections of gravitational waves by the NSF-funded LIGO facilities, this work shows that consistent investment in basic research pays off. This result is the first of its kind. We have never before used multi-messenger astrophysics to pinpoint the origins of high-energy cosmic rays. I want to commend the researchers for how they've presented this to the world. The experimenters take care to quantify the statistical significance of the spatial and temporal coincidence of the high-energy neutrino detected by IceCube and a blazar flaring in gamma rays. Like Hess's discovery of cosmic rays, these first results will raise new questions and open doors for new research. As in all good science, this is only the beginning, and that's exciting. Now, let's hear about the new updates from today's presenters. I'd like to welcome Frances Halsen, Principal Investigator of the IceCube Observatory at the South Pole, Regina Caputo, Research Astrophysicist at NASA's Goddard Space Flight Center in Maryland, Razmik Mirzoyan, Senior Astrophysicist at the Max Planck Institute for Physics in Munich, Germany, and Olga Botner, Professor of Experimental Particle Physics at Uppsala University in Sweden. First, Dr. Halsen.
After the director's introduction, I think I should show a picture of Victor Hess, who just ascended to 17,000 feet without oxygen. He discovered cosmic rays, which are not rays, they are nuclei, mostly protons. And we don't know where they come from. We have been seeing neutrinos since 2013, and we still didn't know where they came from. It's one of the oldest open questions in astronomy, and of course the issue fascinates particle physicists because cosmic ray accelerators routinely accelerate particles to 10 million times the energy of the Large Hadron Collider beam in Geneva. So to track cosmic accelerators, that was actually always meant to be the flagship mission of IceCube. We transformed a kilometer cube of ice a mile deep under the geographic South Pole, under the Amundsen Scott National Science Foundation station, into a neutrino detector. And it's very simple. You fill a kilometer cube of ice with 5,160 light sensors, and you detect neutrinos. So this is a neutrino, an optical module, an optical sensor, starting a trip probably 2,400 meters deep, and that's the last time you see it. So why neutrinos? This is like a theorist image of a cosmic accelerator, a black hole of some kind, and it managed to transform some of its gravitational energy into accelerating particles. So there are accelerated protons because it's a cosmic ray source, and they will interact with the light in the galaxy and with the hydrogen and produce neutrinos. So the goal is to track cosmic ray sources by looking for neutrinos. And so they will point back, they're neutral particles, they will point back at the source. And on September 22 of last year, that's exactly what one neutrino did. And you can see it coming through the ice, lighting up the sensors. In fact, you don't see neutrinos. What you see here is a muon, which is a particle that was made by a neutrino somewhere to the right of the detector, and that streaks at the speed of light through the ice, lighting up the sensors by the blue light that it emits. So within 43 seconds, the computers at the South Pole captured these signals, reconstructed the energy and the direction of the track, and sent it for any telescope in the world that would be interested in it. This is the event. And so what we found out is that sometime later, if you look at the picture on the left, within 0.06 degrees, Fermi was aware of a source, an active galaxy, that actually was flaring. It had, in the last few months, increased its output, its power, by a factor of more than 6. Subsequently, the MAGIC telescope that detects the highest energy form of gamma rays that we detect in astronomy, detected that the source emit TV gamma rays. This is a very unlikely event. So by then this was interesting, and more than 20 telescopes, which are shown on this slide, looked at the direction of this event. So that's, however, only the beginning, because now we knew of an interesting place in the sky. Both Fermi-LAT collaboration and the IceCube collaboration, we have stored some 10 years of data on tapes and now disk. And we can go look back in this direction, and that's what we did. And while the event I'm talking about was dominated by essentially one 290 TeV neutrino, when we look back in our data, we found that in 2014, there was a flare in neutrinos, more than 12, that came in 150 days. when we measured the energy distribution, the energy pattern of the neutrinos, is exactly that what we expect from cosmic accelerators. In fact, that's the same is true for the gamma rays in 2017 and 2014. So what did we discover? Well, we finally discovered one source of cosmic rays. It's a supermassive black hole that powers the accelerator and produces the neutrinos and the gamma rays subsequently detected. This is only the beginning, but through this campaign, we have collected an incredible amount of data on this source, and most important, we know it accelerates protons and not just electrons. So this is actually not the first time multi-messenger neutrino event occurred. It occurred in 1987 when a supernova exploded in our local neighborhood. But who could have guessed that we would stand here 30 years later and report a similar event with neutrinos that are 10 million times higher energy from a source that's 100,000 times further away in the universe. So to tell you the rest of this story, I'd like to introduce Regina Caputo, who is the analysis coordinator of the Fermi-LAT collaboration.
Thank you, Francis. It's a privilege to be here today speaking on behalf of the Fermi Large Area Telescope collaboration, a collaboration of over 400 scientists from around the world who are constantly monitoring the gamma ray sky. So the object that we're talking about today, as you've heard a few times already, is a galaxy. And this particular galaxy has a very dense core at the center. And at that core is a supermassive black hole that's millions to billions the times of the mass of the sun. Now, it's surrounded by gas. And what you're looking at in this visualization is this central core of a galaxy. As we go in, you'll see this gas that gets gravitationally compressed into a disk and gets accelerated and swirled around this central black hole. Now, sometimes these particular galaxies shoot out jets of particles. These blazar jets are true cosmic accelerators, and they accelerate particles to the highest energies, higher than we can see on Earth. Now, when that jet is pointed at us, that's what we call a blazar. Now, the Fermi Large Area Telescope, or the LAT, observes the full sky. And the scientists who analyze Fermi data are constantly checking for objects' variability and changes in that gamma ray sky. And so what you're looking at here is an image of the northern hemisphere of the galaxy in gamma ray data. And you'll see a time-lapse image over about 8 months of these flaring objects. So you see they change, the flux changes and flares and increases. And what are circled are the 11 most energetic blazars that we observe. We actually observe over 2,000 blazars in the gamma ray sky. So this particular blazar, called TXS 0506, is located in the Orion constellation, but it's about 4 billion light years from Earth. Now, if you are looking at the sky at Orion, this is about what you would see with your eyes. But the way that we see it in gamma rays, and we'll go ahead and outline Orion as a reference, you see it's the source right there under Orion's arm. Now, this particular source is a bright Fermi source. We've seen it for 10 years. And starting in April, it experienced one of the largest flares that we had, well, the largest flare that we had ever seen from this particular source. Now, Fermi is on orbit in space, which is probably the only place that's more inhabitable than the South Pole. And what you see is gamma rays coming in the magenta squiggles, formed in the same place as the blazar jet with the neutrinos. And Fermi detects gamma rays, as you can see illustrated when it lights up in magenta, although it doesn't actually do that. And the neutrinos sometimes pass straight through the Earth. Now, just to give you an idea of what this source looked like for the first 10 years, we have a time-lapse video showing the gamma ray data as represented by these circles, where the size and color of the circle is representative of the energy of the gamma ray that entered. And so you could see, we see lots of gamma rays from this source. It's an active source, it's bright. And this is what a typical emission state looked like. Then, because we're able to monitor the sky all the time, we were able to notice that during April, which starts right now, that the number of gamma rays from this source increased by a factor of more than 6. So it was very, very crazy emission from this source. And I've stopped it on September 22nd, 2017. And you'll see just how bright this source was in gamma rays as represented by these circles. And so it was really, really exciting when we got the notification from IceCube, because as I've mentioned, blazars flare, but the fact that we could tie together the gamma rays and the neutrinos tells us something very exciting about the particle jet and the particles that are being accelerated. So we've now entered a new era, starting last year with the joint discovery of gravitational waves with gamma rays from Fermi. We were able to view a cosmic explosion when 2 neutron stars merged, and we were able to detect it in these multi-messengers. Today, we're really excited to report. Now we know something about cosmic accelerators in the joint detection of neutrinos and gamma rays. And so to give you more information about the 20 observatories that followed up this very exciting notification, I'd like to introduce Dr. Razmik Mirzoyan from the MAGIC collaboration, who's the MAGIC spokesperson. Thank you.
Good morning, ladies and gentlemen. I feel privileged to be today here and to talk from the name of the MAGIC collaboration and to talk about measurements done by MAGIC in this big event, in these multi-messenger detections. In astronomy, we are observing objects at different wavelengths. You can see, just as an example here, I show you SEN-A, the source observed in X-rays or in optical wavelengths, in the radio continuum. And then you can see that the source is looking very different depending on at which wavelength it is observed. And then this multitude contains a lot of information which allows us to understand the source nature. But now imagine there is a multi-messenger detection, a neutrino is coming into the game. And I should tell that I can remember something like 25, 30 years ago, many discussions with my colleagues, with my friends, and they were saying sometime in future, maybe it will become possible to measure sources not only across the electromagnetic spectrum, but also maybe one can measure with ground-based instruments neutrinos. And I'm very happy because today it's becoming reality. On 22nd of September 2017, IceCube set an alert for an extremely high energy neutrino. And a few days later, Fermi collaboration measured a signal from a particular direction, practically coinciding with the direction indicated by IceCube from an object with the name TXS 0.0506. And then that was followed with other measurements, MAGIC telescopes, measured on during 12 hours, a strong signal from the same direction like Fermi has indicated, and this was followed by an avalanche of other detectors, almost 2 dozens of instruments across the electromagnetic spectrum worldwide measured signals. So This is the MAGIC collaboration. It's a middle-sized collaboration consisting of about 175 astrophysicists. And 2 weeks ago, we were celebrating 15 years of anniversary of operating our instrument on the Canary Island of La Palma. So these are the two MAGIC telescopes, which are located on the Canary Island of La Palma at an altitude of 2,200 meters above sea level. And this is very different from what Regina has described and Francis has described. We have nothing to do with the ice in the South Pole or high up satellite mission. I think this is La Palma is well known as a resort place, a place for doing vacations. So we are enjoying having vacations and doing science together. And we try to do it very efficiently. These two telescopes, they have a 17-meter diameter each. They have a focal length of 17 meters, and they are separated on 85-meter distance from each other. And these are really high-tech telescopes. They introduced a lot of new techniques and methods into the field. One of the distinguishing features of these telescopes is we can rotate them very fast. Within 20 seconds, we can go to any direction in the sky, and this is very crucial when a fast alert is coming, like the one from IceCube. So in this cartoon, I would like to give you an impression what we are measuring with these telescopes, because the telescopes are somewhat different from usual optical astronomy. Our Earth's atmosphere is not transparent to gamma rays. They will be absorbed very fast. Somewhere on 25-kilometer height, gamma rays get absorbed. But then they produce secondary particles. And the secondary particles, mostly electrons and positrons, they move with a speed higher than the speed of light in the air, and they emit this bluish light, this blue color light. So these telescopes are measuring this, collecting this blue light, and then focusing it into the focal plane, where an imaging camera will measure the shape of an air shower in the atmosphere. And then based on this shape, we can measure the energy and then most parameters of these gamma rays. This is how these telescopes are working. Here I would like to show to your attention a cartoon. This cartoon is about an attempt to understand how these multi-messenger detections happened in total, to have a big picture. So for understanding this picture, I would like to tell you that today there will be published 7 papers devoted to this event, and I'm expecting that an avalanche of papers will follow in the next times. But from these 7 papers, 2 will be published in the Science magazine. There are 5 more papers. So it is an attempt of a accompanying paper from a MAGIC collaboration, where we try to talk about the blazar. You see the jets of the blazar, and then you can see zoomed in jet. And then under special conditions, I think you can have relatively low energy photons, and these photons can interact with electrons, and then due to this interaction, so-called via inverse Compton mechanism, you can get gamma rays, but also protons are there, and these protons can interact with these photons, and then they can create, via photomeson production, they can create pions, which will later on decay to neutrons. So you look to the picture, you see the red color as the protons, and because of the charge, they move in a zigzag line, so they deflect in the different magnetic fields. So when we measure protons, we cannot say the incoming direction, but you pay attention to the green line. These are neutrinos, which are detected by IceCube at the South Pole, and you pay attention to the blue lines. These are measured by Fermi satellite and then MAGIC telescopes. These are gamma rays. So I think we try to get a consistent picture, and in this picture, I think we can explain very well how it comes that we can measure simultaneously neutrinos and gamma rays in different energy ranges. And then when you measure neutrino is a smoking gun for a parent proton. So if we measure about 300 TeV neutrino, it means that there is at least order of magnitude high energy proton. So these protons are in the jets of blazars, and this seems to be the first time that we can say something serious about the long-standing question where the protons are accelerated, and protons are nothing else other than cosmic rays. So it means that blazars can contribute cosmic rays at extremely high energies. This is a very strong message. And with this message, I would like to give the word to my colleague, to Olga Botner, former spokesperson of IceCube collaboration. And she is going to present details of the accompanying paper of IceCube collaboration, second paper in the Science magazine. Thank you very much for your attention.
So it's a great pleasure for me to stand here in front of you on behalf of the IceCube collaboration. 300 scientists from 12 countries around the world on 4 continents, and most of them young and not gray-haired like Francis and myself. 300 sounds like a lot, but the number underscores the tremendous effort which has kept the dream of neutrino astronomy alive for the past 3 decades. From the tentative beginnings around 1990 to the proof of concept with the Amanda prototype array at the South Pole, of highly energetic cosmic neutrinos with IceCube in 2013, to today's exciting news, the first evidence for a source of such neutrinos. As you've heard several times today already, IceCube's September 2017 alert, in association with gamma-ray observations, pinpointed an astrophysical object named TXS 0506 and sometimes nicknamed the Texas source as the most likely source of these neutrinos. And what you are looking at on your right-hand side is a picture of the sky at radio frequencies at the position of the blazar. And you are, as it were, looking directly along the barrel of one of the blazar jets. That's the bright white spot at the center of the red blob. Now, intrigued by this association, we decided to look in our archival data to see if we could identify any more neutrinos coming at us from the position of this source. As you may know, IceCube was completed in 2010, but we had been taking data in partial configurations already for several years before that date, and so we had about 10 years of data to scrutinize. And, amazingly, we discovered a neutrino flare centered on December 2014. During a period of 5 months, we observed 19 events where we expected about 6 events from cosmic ray interactions in the atmosphere. This is an additional bit of evidence indicating that the blazar is indeed a source of high-energy neutrinos. What I'd like to do now is to play a movie for you, a movie showing how the neutrino signal accumulates over the 5 months. So here goes. From nothing to a peak and disappearing again. And on your right-hand side, you see a timeline with the neutrino intensity as a curve and the arrow indicating the time interval of this movie. I want to just show you the intensity at the peak of the flare again. So this white spot, the bright spot in the center of this sky map at the position of the TXS is the neutrino flare. So as I've just told you, we detected 13 neutrinos, which we believe are signal from the direction of the Texas source in the 2014-15 flare. During these 5 months, 15 million neutrinos at similar energies and from the same direction passed IceCube unseen. And this ratio 13 to 15 million illustrates very well how hard it is to catch a neutrino. A neutrino is invisible unless it collides with an atom, and this happens very rarely. And so you need to monitor a tremendous lot of atoms to stand a chance to catch a neutrino. IceCube at NSF's Amundsen Scott South Pole Station instruments a volume of 1 cubic kilometer of the clearest glacier ice. This is 1 billion of tons of ice. 10 to the power 38 atoms. This is a 1 followed by 38 zeros. On your left-hand side, you see how the ice cube sensors, like the one which is standing in front of you on the podium, are attached to cables, deployed into vertical holes drilled by means of hot water, and left to freeze in the ice. On your right-hand side, you see a neutrino coming from the bottom right, colliding with an atom, producing a charged particle, which is called a muon, which then moves through the entire depth of the detector, trailing a cone of bluish light. And it's this light that our sensors detect. Now, the colors you see in this picture are not the colors of the light, but they illustrate the time sequence of the signals we observed, with the reds and oranges being early and the greens and blues late. So as you can see for yourselves, from the time sequence, we can reconstruct the direction of the muon and hence the direction of the neutrino. So this is how we know that the neutrinos we observe come from the TXS source. In 2013, IceCube made a breakthrough discovery of a diffuse flux of highly energetic astrophysical neutrinos. Since then, we have observed a couple of hundred such events. And what you see in the upper panels on this slide are the 4 highest energy neutrino events ever observed on Earth. What you are seeing is not the neutrinos themselves, but the light images as they are recorded by IceCube. And to give you some kind of feeling for the dimension, think in terms of hundreds of meters or kilometers. On the picture below, you see the directions of these high-energy neutrinos distributed over the sky. And as you can see for yourselves, there is no obvious accumulation of directions. So the million-dollar question has since then been, where do these neutrinos come from? And for the neutrinos we're reporting on today, we know the answer. We needed electromagnetic observations to assess the association of the September 2017 alert with an astrophysical object. The neutrino burst in 2014-15 strengthens this association. And so the bits of the puzzle are starting to fall into place. For the first time, we have been able to associate high-energy neutrino emission with a high-energy gamma-ray source. This is what we've been waiting for. This is the first evidence for a high-energy cosmic accelerator, a pivotal moment for multi-messenger astronomy. Now, as you see in this graph, on your left-hand side in the bottom corner, I show also the gravitational waves. And as most of you know, we have not identified neutrinos in connection with gravitational wave events yet. But we believe that this is the discovery waiting for us just around the corner. Thank you.
Well, there you have it. So now we're open for questions.
Hi, this is Emily Conover from Science News. I wonder if you could talk, you've got one neutrino now that's associated with this blazar. What's sort of the future of this kind of work? How soon can we expect another one? I mean, obviously that's hard to predict. But, are there any plans for future upgrades that might increase the rate, things like that?
Okay, well, first I'll have Olga just clarify that there's actually more than one, and then ask Francis to address your question.
Yeah. So just to make it quite clear, there is 2 papers published in Science. One is the paper about the 2017 alert, and this is one high-energy neutrino pointing at the spot in the sky. But then in our archival data, we have more than a dozen neutrinos coming at us from the same direction. So we have actually a handful of neutrinos from this object. And this is why we are confident that this is a source of neutrinos and a probable accelerator of high-energy cosmic rays. Now, about what we would wish for the future, this is, of course, a good question. And I've tried to explain that neutrinos are very, very difficult to catch. So, to get more, you need a bigger detector. And I let Francis continue on that.
Well, the short, direct answer to your question is, you saw it actually on one of Olga's plots. In the last 9.5 years, we saw 2 bursts. And that's the only information we have right now to predict when we'll see the next one. The key, I think, is this source is very special because, why do we detect the first source 10 times further away where there are very nearby sources? And so the key is to find other sources that do this. And then hopefully you can beat this 2 times in 10 years time scale. But as usual, the work has just begun.
Francis, are there plans, just following on that question, are there plans to make the IceCube observatory bigger?
Of course.
That's the answer she wants.
And I'll just add to that, you also want to keep continuing to monitor other high-energy particles like gamma rays to have these joint detections, because so you want to continue to monitor the gamma ray sky as well.
Great. And once LIGO is up and running again, right now it's being refurbished to have higher sensitivity, which is really important in these things, then we can see, as Olga said, the last piece of that puzzle falling into place in multi-messenger astronomy. Another question, please.
We have a follow-up. Sorry, I just wanted to ask about the when you look back in the data and you see the neutrinos, this handful of neutrinos, is there any evidence of a gamma ray flare at the same time or anything like that?
So there's 2 things you basically have to look for: the number of gamma rays and the energy of the gamma rays. And so at the time of the neutrino flare, we didn't see an increased number of gamma rays, but there is some evidence to indicate that we saw an increased energy in the gamma rays, because they're produced at the same time. The same process that produces neutrinos also produces gamma rays. That's why the energy is also important. So we didn't see an increase in the flux, which is why, and we didn't have an alert from IceCube, but also Fermi, all of the data is archived, so we can go back and look at the data and see what was happening at the same time.
May I just add a sentence? I mean, this is actually very exciting, right? It's not clear-cut science. We are learning about the blazars as we go. They don't, it's not as it was predicted. It's not as we had expected. There's more things going on, and we are learning new things. So this is just the beginning.
The physics of jets, just so you don't think that that's all been figured out, is really has a lot of mysteries in it. And this is another piece, as Olga's just said, of the puzzle of how do particles get accelerated to these tremendously high energies in these kinds of environments. And as I said in my opening remarks, this is so much higher energy than what we can produce on Earth in our best accelerators. Another question.
Yeah, hi. Arthur Friedman, the UCO reporter. So I'm wondering, are the neutrinos traveling at the speed of light? And the other part of the question is, if they were in a gravitational wave, would the gravitational wave accelerate them even faster, or are they already at the maximum speed? I was just trying to understand the interaction if they were a part of a gravitational wave, but undetected so far.
Thank you. Francis?
No, I mean, when we say they travel at the speed of light, of course, it was a major discovery in '98 that neutrinos actually have a small mass. But this mass is so small compared to the energies ice cube is observing is totally irrelevant. So neutrinos are basically like photons. And so there's no difference. I don't know if this answers your question. I'll give you an example of an event where we would see neutrinos and gravitational waves. And we are all waiting for it, as I said. 30 years ago, an explosion and a collapse of a star, unless it were perfectly symmetric, would produce gravitational waves. And we know that we can see neutrinos. So that's one case. The neutron-star merger, which is still on the screen, actually make jets. When they spiral in, a jet is formed, which is very similar, actually, in concept to what we are talking about here. And presumably, this source emits neutrinos in some similar mechanism than the blazars. And of course, the jet in that event was seen in gamma rays.
So Razmik showed an illustration of the first cosmic neutrino detection of supernova 1987A, and we didn't have gravitational wave detectors at that time. So it's all just coming together as the technology increases and we have more opportunities to do these multi-messenger observations. Another question, please? So you're all ready to take an exam on this, you know, it's...
I have a question from the web.
From the web, okay.
In light of the breakthrough results from small-scale, high-impact experiments like QWEEK and EDGES, why does NSF invest in expensive projects like IceCube when the funds could support a wide range of smaller yet still impactful efforts?
Well, I hope we're investing in both small tabletop experiments and these very large kind of experiments because they can detect different phenomena. But let me ask our observers here their thoughts about this question.
I think this is your job.
Okay. All right. Okay. No, the creativity that is out there is just immense. We recently had a call for information on what people were thinking about doing in the smaller line of experiments. And we got $10 billion worth of responses to that question of all kinds of imaginative experiments that can be done. So we just, as a country, need the will, the imagination to go after that and to invest in the creativity that's out there.
Another question. Quite simply, why does this research matter?
Okay. Mysteries matter, right? So a lot of us probably started out wanting to be detectives when we were very young, and I know that's what I wanted to be because mysteries captivate all. How many of you watch mysteries on shows? And that's and this is when you get to mysteries of the cosmos on a grand scale. That's really magic, and as we've been all talking about, our experimenters here, that this is one of the most, this is a mystery that's 106 years old about what's the origin of high-energy cosmic rays. Where do they come from? It's just, these are inconceivably high energies, as we've been saying, produced higher energies than we can even produce in these extremely wonderful big accelerators here on Earth. And going after those mysteries, whether it's dark matter, dark energy, the origin of cosmic rays is what really science is all about, is uncovering the mysteries of nature. But I'll let my experimenters
I would like to add to that, because actually learning about the universe and understanding nature is the basis of our societies. This is what we are building on. Right? If we're not curious about how nature works, how the universe works, we would still be living in caves and be afraid of the thunder, right? Mm-hmm. So, the fact that we want to understand nature and want to put to use our understanding to build the welfare of our societies, I think is a very, very important point behind the science we do.
But I'd also add, I think it's twofold, because humans are naturally very curious and we need to ask these questions. But in the pursuit of answering these questions, we develop new technologies that has applications that we can only begin to understand through their development. When the electron was first discovered, we had no idea we could use it for electricity. And that's, what powers everything that we do. And so I think this even touches back on that initial question of why invest all this money when you could invest smaller amounts. And it's because sometimes the biggest breakthroughs require us to invest a lot in technology to answer the biggest questions.
Great. Last question. What does this discovery mean for the future of astrophysics, multi-messenger astrophysics, and NSF support for facilities and research?
Well, I think this last slide that we have up here is just a perfect way of saying we haven't yet done the ultimate multi-messenger detection of using, bringing together gravitational waves and particles and electromagnetic radiation. So we have exciting work there. The things that we are discovering, like with the LIGO observations, these huge black holes and binary systems, neutron stars merging, things that were imagined but not witnessed. And so we have a tremendous amount that we don't yet know about the universe. Not only things like blazars we knew existed, and we knew that there were all sorts of mysteries connected with them. We hadn't confirmed the association yet with the cosmic rays and the high energy neutrinos, and that's now been done and is announced today. But there are many other things out there that we have no idea that even existed, as the LIGO observation showed. And so we have just much, much more to discover about our universe and our place in it. Again, Francis.
Yeah, there's something that is rather difficult to explain, but and that hasn't been mentioned today, but we learned something from the diffuse flux of neutrinos that were discovered in 2013. In fact, that flux we detected is very large, which is difficult to imagine when you realize it's like one event per month or so. But if you look at the energy density, remember, for every neutrino that goes through, there are 100,000 we don't go through for the one we catch. So you look at the energy density in the high energy universe in neutrinos, it's roughly the same within a factor as the one in gamma rays. And these neutrinos come from proton sources. So I think this is going to make an impact and a serious rethinking of the way we understand the non-thermal universe.
Yes. Wait 1 second for the microphone, please.
Hi, I'm Dennis Ollier, a freelance science writer. Are there any other potential messengers out there besides the 4 that you have up in that package?
I guess ones we haven't discovered yet.
But nothing in theory, right?
Dark matter.
Nothing in current theory, right?
Dark. I mean, I guess the audience is we're pulling the audience now. No, I mean, discovering, the particle nature of dark matter. I mean, that would certainly be another way that we can investigate the universe. So, certainly, yes, the audience.
Sterile neutrinos.
Yeah.
But I don't want to bring it up.
You'll get everybody's imagination working here. All right. Any other questions? Now's time to ask. All right, so we will convene our experimenters in, as Amanda said, in the back room there, where reporters can ask them additional questions. And thank you, everyone, very much for being here this morning to hear this news.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond. It's all about matters of the heart. Hi, I'm NASA astronaut Tracy Dyson. Welcome to Station Life. The focus of today's show is on matters of the heart as they relate to good cardiovascular health. We'll take a look at how NASA keeps astronauts' hearts healthy off the Earth. And we'll take a look at some of the research being done aboard the International Space Station that can keep all of us healthier here on the Earth.
Houston on 2 for velocity confirmation. You can go down to steps 4, 5, and 4, 6. We're moving on to step 5.
You will go right now for that activity.
Copy. Thank you.
Okay, Tracy, we copy, and that's good information. We'll pass it along.
Cardiovascular disease, including heart disease, stroke, and high blood pressure, is the #1 killer of men and women across America. Fortunately, many studies have shown that healthy habits, including good nutrition and exercise, are important for maintaining a healthy heart here on Earth. Those habits are even more important for astronauts on the International Space Station. Living in microgravity for 6 months changes our bodies in a number of ways. Without gravity, we lose bone mineral density, our muscles atrophy, and our cardiovascular system gets weaker. Some of our studies have shown that in space, the size and shape of our hearts may actually change, which could make it difficult to do our jobs when we get back to Earth or even land on Mars. On Earth, our heart and blood vessels are well adapted to work against the downward pull of gravity. In space, however, there's a tendency for blood and other bodily fluids to accumulate in the upper body. Let's take a look at one of the consequences of this fluid shift.
We have recently identified that some astronauts experience changes in their vision, which might be related to the cardiovascular system. Our hearts pump blood around our body through blood vessels. Special adaptations in our bodies ensure that fluid is evenly distributed despite the pull of gravity. In space, astronauts no longer experience the downward pull of gravity, and the fluid in their bodies tends to move towards the upper body and the head. Our cranium is a rigid container. As the fluid moves towards the head, it causes the pressure inside the skull to rise. This is known as increased intracranial pressure. The optic nerve travels from the brain to the eye. The increased pressure from the cranium travels down the nerve and affects the eye. It causes the optic nerve to be squeezed and the optic disc, where the optic nerve meets the eye, to swell. The back of the eyeball flattens as pressure builds behind it, and the blood vessels in the back of the eyeball also swell. These changes can affect the astronaut's vision. One change is that the astronauts become farsighted. A second change is that they can develop cotton wool spots, which represent damage of the nerve fibers in the back of the eye. These can cause discrete areas of vision loss. NASA is working to understand and prevent these changes in astronauts, which may also help us understand and prevent related vision changes here on Earth.
One of the tools we have to study heart health aboard the space station is an ultrasound device, which uses harmless sound waves to take images of the inside of our bodies. Those images can be viewed at the same time by researchers and doctors in mission control. With minimal training on the ultrasound, remote guidance techniques developed by NASA enabled astronauts to take detailed images of their own heart. In our next segment, we'll travel to a small community in Brazil that has benefited from remote medicine techniques that were advanced by the research aboard the International Space Station.
Minas Gerais is a large state. Our territory is about the size of France, and we consist of 853 units and municipalities. There are large distances between our communities and many very isolated rural communities. We are using new technology that impacts the quality of prenatal care and the diagnostic capacity of the primary care doctor in these situations involving distant, isolated communities.
Providing medical care for people in remote locations, like distant rural communities or the International Space Station, can be difficult, because trained medical personnel are not always available. NASA research teams develop techniques that enable astronauts aboard the space station with minimal training to operate an ultrasound device using simple printed guides. The ultrasound images are transmitted in real time to a doctor back on Earth, who can make medical decisions without actually being aboard the station. These same techniques have been adapted for use with portable ultrasound devices in communities where expert medical care is not always available.
We are also incorporating the first aid and emergency care components, improving first aid at the scene of the accident and enabling the use of ultrasound to communicate to the medical communication center. In the ambulance, we can use ultrasound in various situations. In those situations where time really matters, in which you have little time to make decisions. The idea of using ultrasound for healthcare is like an extension of the physical examination. You are able to conduct the exam with much more detail. And you can use it at the time to make a decision, or you can use telemedicine platforms to obtain a second opinion from someone at a distance. My name is Joaquim Diniz. I'm a doctor in the town of Manga. In Manga, people live with a particularity, and that is isolation. We have a geographical barrier, that is the São Francisco River, which is both a blessing for the region, but it also isolates us. We live in a region where financial resources are few. People do not have a lot of work, but they are honest, good people who do not have much opportunity. So there are many needy people who need these resources and rely only on this institution to provide assistance. This is a technology that helps us solve many problems. That was the case of a patient who came to the hospital with severe respiratory failure, and the people realized she would die in just 20 to 30 minutes. We talked with Dr. Parzelli, who was training us to use the ultrasound. He came and applied the ultrasound and discovered large amounts of fluid around her lungs and heart. We performed the procedure and drained a lot of fluids. In 10 minutes, the woman immediately experienced an improvement and in half an hour was already walking. It was like a miracle, a rise and walk. She was dying in front of us without people knowing what was happening. This ultrasound was instrumental in saving the life of that patient.
All right, ladies and gentlemen, boys and girls, space geeks from all over the world, we have with us today a real treat. Dr. Koichi Wakata from the Japanese Space Agency and absolutely one of my favorite astronauts. Actually, in fact, wait a minute. I have a list right here, and I want to prove it. Look, Koichi.
Oh, great note.
TC's top 10 heroes of space travel. Look.
Wow.
He's on there. Welcome, Koichi.
Good to see you, Tracy, here.
Nice to see you too. Thank you for joining us on Station Life.
My pleasure. I'm always watching your program.
Really?
I'm glad to be here.
Oh wow! Did you hear that? I am so excited that you. I'm actually honored that you watch our show. It's all about the space station, you know.
Yes. Yes, this is wonderful to be able to explain how wonderful it is to work and live on board the space station.
Yes.
And then today, what are we talking about?
Today we're talking about cardiovascular health.
Awesome.
Yes. And you know a thing or two about that.
Yes, we do exercise pretty much every day.
I was going to ask you on board, did you work out every single day?
I did, because it's not only, to keep, my body healthy, but also it's a very important psychological, I think, relaxation for me. And then the best part of the exercise is the, what is that? The air-raid device that we have on board.
Yeah.
It's just sitting right next to the cupola windows. Yes. It's probably the best view gym in the entire world, I think.
Absolutely.
Yeah, you can do the, muscle strengthening exercise, and at the same time, you can see this beautiful, home planet. And what a wonderful place.
That's right, because we have the cupola and we have that big center window. We call it Window 7. And then most days, because the space station is oriented with the belly of the space station facing the Earth, which means that the cupola windows are facing the Earth. And there we are on the A-red, above it, below, however you want, whatever your perspective is. But anyways, we're right in line looking out that window, which seems to us like we're on a bench. We're doing our bench press and we're looking out that window. And I remember doing my exercise one day and I saw red soil go by and I'm like, that's Australia!
Exactly.
So yes. You can practice geography at the same time. Can you tell us a little bit about Sprint and what that was all about?
Right, Sprint exercise is a new protocol, and already several astronauts have tried that method. And basically, it uses the prescription of like a higher intensity of exercise, but less volume or less number of exercise days. For example, like if I on board the space station 7 years ago, I pretty much exercised like running for 40 minutes in the same pace. But here, as far as cardiovascular is concerned, we have like a sprint running, like for 30 seconds sprint, and 15 seconds rest, another 30 seconds of run. But it's only like 6 or 7 minutes, very short interval, but high intensity training. And you do that like 3 times a week instead of 7 days a week.
Wow.
And so it's like a smaller number of days of exercise, but the higher intensity. And that's part of the sprint protocol. So 7 years ago when I was on board the space station, I used the previous protocol, which I exercise every day. But this time, it's a smaller amount of time actually. But the results were pretty good. I was able to walk right after landing, and so I think this new protocol is working very well.
Wow, so if you compared when you were on board and landed 7 years ago to now, when you did this new protocol and you exercised more and you had probably more emphasis on the exercise because you have more equipment to work with.
Right.
A big difference, did you notice?
As for after landing, I don't see very much difference. So that means that's such a very efficient way to do exercise, because if the results are the same, if you spend less time and exercise, that means it's a very efficient way of exercising. So maybe we can utilize that in the future when we go to beyond low Earth orbit, when we go to Mars, and then so a lot of new protocols are being tested on board the station.
Yeah, and I can see where folks back here at home who don't have time to exercise pay attention to this, because you can spend less time working out and get the same benefits as if you were working out for 2 hours or something.
Right.
And you have done just a tremendous amount of work, Koichi, not just in your most recent increment, but throughout your career in the space program, and you've been an asset to Japan and to NASA and to the International Space Station and to Station Life. So thank you so much for being here with us, spending so much time sharing your stories. We've just had a lot of fun with you. So wish you all the best as we go forward. I'll see you, probably in 5 minutes, but, thank you so much for being here with us.
I enjoyed it. Thank you, Tracy.
Likewise.
Glad to be here.
Cool.
I think they can actually put ice in here. much water pressure we have that day. We can do 60 to any ml at pretty much any time. If we have good water pressure, we can get you up to around 80. But you're saying Tracy's taking all the phone. So you're the one I'm going Okay. Thank you for that.
So with all this exercise going on, is it really working? Researchers and ACERs, who are astronaut strength conditioning and rehabilitation specialists, have made great progress. Before we had a full gym on the space station, our astronauts needed quite a bit of recovery time back here on Earth. Today, our astronauts are coming home in excellent health.
My name is Mark Williams. I'm the lead astronaut strength and conditioning coach. On board at the International Space Station, we have 3 pieces of hardware. We have a cycle, which we call CVIS. We have a treadmill, which is called T2, and we have a resistive exercise device, which is called ARED. And each device is specifically designed to do certain things for the astronaut. We try to do one of those particular devices every other day. One of them we're going to get a little bit better cardiovascular fitness out of it. The other one we get a little bit more impact loading, like running on the ground. So that affects muscle, it'll affect a little bit of bone, does things. Those are the physiological aspects of it. But then also making sure when they come home from a 6-month flight that they don't come home like a bowl of Jell-O. You know, they're going to lose muscle, they're going to lose strength, they're going to lose bone, they're going to lose cardiovascular fitness. But at the same time, then we have to take them, get them back to where they were before they left, which is what we do in our post-flight period once they come home for about 6 to 8 weeks, and just get them prepared back to normal life, you know, doing their job, doing with their family, doing yard work, whatever that happens to be.
Have you ever been sedentary for a long period of time, like lying in bed for a week because of an illness or surgery, and then stood up quickly? Did you feel like you might fall or that not all your senses were functioning? Hi, I'm Dr. John Charles with NASA's Human Research Program. During the 1-year International Space Station mission, NASA will conduct functional studies to gain insight into key physiological factors that contribute to changes in performance. Just like it would take minutes, hours, or even days for your body to acclimate to standing after lying in bed for weeks, it takes time for an astronaut's body to acclimate to an environment with gravity after working without it for many months. 2 tests will focus on post-flight tasks and procedures that will be vital for an exploration crew that has just landed on a planet after a prolonged period of weightlessness. The functional studies will assess how the neurosensory networks, eye-hand coordination, fluid distribution, cardiovascular, and skeletal muscle performance all work together to accomplish an integrated task or function. Researchers hope to compile a post-flight recovery timeline and develop and validate tests to define acceptable performance and define the linkage between physiological changes and functional capacity. This information will be helpful for astronauts and researchers as they prepare for future long-duration missions to asteroids, Mars, and beyond. To learn more about NASA's Human Research Program, visit www.nasa.gov.
So now let's hear from one of our researchers who is studying the cardiovascular system off the Earth for the Earth.
My name is Stuart Lee. I'm the lead research scientist in the Cardiovascular and Vision Laboratory at Johnson Space Center. So the astronauts in spaceflight is somewhat analogous to if you took one of us on the ground and told us not to exercise for a long period of time. So spaceflight has allowed us to see the deconditioning effects, and we can see all the negative things that can happen when you don't exercise, when you don't do physical work every day that we're actually genetically designed to do. So I would say that cardiovascular health is important from the aspect of the heart and the blood vessels are the communication system in your body. So the experiment that they're demonstrating in the background is the primary measurements in our cardiovascular experiment called CardioWalks. And it's primarily looking at the health and function of the arteries in your body. In this particular case, they're scanning the brachial artery, and we use that as a surrogate for the arteries in your heart, the coronary arteries. So we're able to see how they would respond to stress. And obviously, if they respond well, then we've got good cardiovascular health, and it has a good prognosis long-term for the health of the heart. So they're looking specifically at how the vessel expands and contracts with each heartbeat, and then we stress the vessel and we see how well it expands. And those are key functions in your ability to adapt to stress when you're exercising or when you're experiencing orthostatic or gravitational stress. And so it gives us a way that we can look at throughout the mission and after the mission how the crew members are responding to the spaceflight experience. So Cardiox is looking primarily at the health and fitness, as you might say, of the arteries. The unique part of Cardiox is we're actually looking at 5 years after the mission. So most experiments just look pre, some in and post-flight. We're actually interested in long-term health of the crew members. 5 years later, were there stresses involved with spaceflight which might have caused some issues for them. Sprint is another experiment that looks at cardiovascular, but it looks primarily at the cardiovascular fitness end of things, how hard you can work. We call it VO2 max or maximal oxygen consumption. How hard you can get your body to work during space. And the VO2 max test is very good because it's an integrative test of the cardiovascular system. It brings together all the function of the cardiovascular system so you can work as hard as possible. So these experiments together give us an idea of what's happening on the functional side of things, the Sprint study, and then on the I don't want to say pathological, but on the health side of things with Cardiox. And then with the Cardiox Twins experiment, we're also then looking at how genetics affects those things. My name is Stuart Lee. I'm a lead research scientist in the Cardiovascular and Vision Laboratory at Johnson Space Center. We're working off the Earth for the Earth.
International Space Station provides an unprecedented research platform in space, allowing doctors and scientists to conduct science experiments that can't be done anywhere else. For NASA, keeping our astronauts' heart healthy is vital for continuing the journey off the Earth. Here on the Earth, the keys to good heart health are good nutrition and vigorous exercise. Thanks for joining us on Station Life at our behind-the-scenes look at cardiovascular research being done aboard the International Space Station. And as always, be sure to follow us on Facebook and Twitter for the latest research news, and download our app, which is legit, on your mobile device. Until next time, we're working off the Earth for the Earth.
Ever think you might want to be a scientist? Or that you could work with NASA? Well, thanks to citizen science programs, you can. Find out how next on Real World. When you picture a scientist, what comes to mind? A person in a white coat? Someone stuck in a lab? Actually, scientists are pretty interesting people doing some really amazing work. And while some scientists do work in a lab, others work in the field, under the water, or on the computer, the one thing scientists all have in common is that they're looking for answers to some serious real-world problems. But sometimes they need help, so they turn to citizen scientists to assist with their research. So what is a citizen scientist?
I think people are aware that NASA has many different missions. We have missions to Mars, we have missions to Saturn, we have many different missions that are observing Earth. There's all this data coming in, and quite honestly, scientists don't have time to go through it all themselves. And we need people to look at this data to tell us what discoveries might be waiting there for us. So this is a way for the general public to do serious, publishable science with us, results that we need.
One of the longest-running citizen science programs is GLOBE, or the Global Learning and Observations to Benefit the Environment program. GLOBE students from around the world conduct research to measure and monitor changes in their environment. These citizen scientists learn to use specific tools before they go out in the field or begin their work on a computer. And they follow a protocol, which is a special set of steps to do their research. Think of a protocol just like following a recipe for a cake. But why are protocols so important?
The most powerful thing about science is that it is a tool to actually discover things about reality. But we all need to make the same measurements in the same way. You have to design an experiment so that anybody, anywhere in the world could do it the same way and get similar results. There's a thing called a scientific protocol, and this means that wherever you are, we're using the same tools with the same precision, and that means we can all compare our results. For example, let's say that somebody asked you to measure the temperature of where you are. Are you measuring in Celsius or Fahrenheit? What time of day did you take the measurements? Did you do it at nighttime or during the daytime? If we simply ask people, what temperature is it, we get all kinds of numbers that don't make sense. But if we specify, it needs to be this accurate, you need to use these units, you need to measure at this time of day, then all of a sudden, we can bring all of this information together and compare it and find trends and make real discoveries about what the world is doing. That's the power of the precision of the tools of science. And that's what a scientific protocol really means.
Citizen science projects may also require you to practice some of your math skills. NASA School, for example, may ask you to estimate the percentage of cloud cover in the sky. Another project might ask for the percent of a leaf that has been damaged by ozone. When the same scientific protocols or steps are used to collect data, that data can be analyzed by scientists to help them better understand the problem they're trying to solve. So what are some other opportunities for citizen scientists to collaborate with NASA?
So which citizen science project should you choose? Well, this is your chance to do a little shopping and let your own curiosity be the guide. The wonderful thing about citizen science is you don't need any special skills to get involved. You, as you stand right now, are prepared to do these projects with us. To me, you really need some curiosity. Are you curious about the planets or about the Earth or the universe? And if you can give us some precision, do the measurements as carefully as you possibly can, that will give us the best results. But you need no special training. Start it tomorrow.
It's pretty easy to get started. Just go to the NASA Citizen Science website, pick a program that catches your interest, then be sure to make careful observations and follow the protocol exactly. Get out there and help. You really can make a difference. See you next time on Real World.
We have been really excited about the NASA challenge. If we actually solve a problem, it would pave the way to engineer large, complex tissues.
We think that we have a solution to a major problem in tissue engineering.
The requirements of this challenge falls directly in line of our ongoing research.
The challenge proposed by NASA and the New Oregon Alliance is the same problem we have been trying to solve for the past 5 years.
We are interested in improving our understanding of vascular bed formation.
Taking the device to the International Space Station and observing how the vasculature expands and creates in the zero gravity environment is extremely exciting.
We think it's really exciting to potentially work with the team at NASA and bring our technology into space. That would be wonderful.
This Week at NASA keeps you up to date. What NASA does, where NASA goes, what NASA finds. From humans living and working in orbit today to future journeys into deep space. From new scientific discoveries about our solar system and the universe beyond, to better understanding our home planet. From improving air travel to developing cross-cutting technologies for future exploration. When you're as busy as we are, a lot can happen in a week. This Week at NASA, on the air throughout the week or online anytime.
It's all about the Earth and what we can learn about it from the International Space Station. Hi, I'm NASA astronaut Tracy Dyson. Welcome to Station Life.
Houston 2 for velocity calculation, steps 4, 5, and 4, 6. We're moving on to
Tracy,
step
you
5.
want to go right now for that activity?
Thank you.
Okay, Tracy, we copy, and that's good information. We'll pass it along.
Welcome back. This month on Station Life, we're going to highlight the International Space Station as a platform for studying the Earth and take a behind-the-scenes look at what it's like to live and work aboard the International Space Station. You know, they say a picture's worth 1,000 words. The first pictures taken by humans from space forever changed the way we view ourselves and our world. If you've ever flown on an airplane in the window seat, you know the natural desire to stare out the window. Well, aboard the International Space Station, one of our favorite things to do during our off time is to stare at the beauty of our home planet.
Take a moment every day to look out the window and appreciate where you are.
Literally watch the Earth go by. We're going around the Earth once every 90 minutes. So you see a sunrise and a sunset every hour and a half.
It's just so vast and so vibrant in color, and so much contrast between the black that it kind of overwhelms you at first.
Don't just look out the window during the day. Go for the times between
day and night and then night and day, and take some time to look out into the universe at nighttime, because that's when you can really see all the stars. And you can see that the stars are not only like in a planetarium where they're sort of in a 2D field, they're actually 3D, and some are farther than others.
But you could see the blues and the oranges and the reds and the whites and the yellows, and really see more color about the stars, which indicates more about where they are in their life cycle, what kind of things they're burning and doing. And you would think that you'd get tired of looking out the window, but you never do.
Like I said before, a picture's worth 1,000 words. But in the case of International Space Station imagery, a picture could also be worth 1,000 lives. An imaging system aboard the station called Environmental Research and Visualization System, ISERV, captured photographs of Earth from space for use in developing countries affected by natural disasters. This is yet another way the orbiting laboratory is serving humanity off the Earth for the Earth.
SOUTENIR is a joint NASA and USAID program where we're working with developing countries around the world and strengthening their ability to use satellites to address the many problems that they have, including floods, fires, harmful algal blooms, and other types of events that they have where they can use satellites to really make better decisions.
We're using space information to help decisions that affect people in the village where they live.
When there's a major disaster, governments around the world come together and they provide all of the satellite data basically that the world has to offer. But there's smaller disasters that occur in the countries that we work in that may not make the front page of the New York Times, but in that country it's a really big deal. We asked ourselves, could we make a difference if we had a dedicated imager for acquiring imagery quickly after natural disasters, and to be able to provide that imagery back to the countries that need them, that have real decisions that need to be made with a very quick turnaround. As NASA, we looked in our own backyard and started thinking, could we use the International Space Station? The International Space Station was really a fantastic asset to take advantage of because it passes over 90% of the Earth's populated area every 24 hours. We developed an imaging system and we called it ISERV, which basically is a camera and a telescope system that sits inside the International Space Station and can collect imagery when it passes over natural disasters or other events that we need to collect imagery.
Initially, we were planning to take a few pictures per day.
So we contacted all the USAID missions around the world, and in total we had more than 2,000 requests coming, for people who need images from ISERV.
And we moved to like 1,000 images per day.
We provided ISERV imagery for many, many natural disasters, including floods and fires, for deforestation, for volcanic eruptions, for earthquakes. So it was really a fantastic example showing how imagery from the International Space Station could be used in these times of dire need.
And now we have a huge archives of images of areas around the world. So this is something that was not really there before.
ISERV is an example of, in essence, making the International Space Station even more international and connecting space to village to better understand and protect our home planet.
Imagine bread loaf-sized satellites zipping around the Earth each day, imaging the globe and providing updates on the environment. Thanks to the International Space Station, this constellation of satellite image gathering has been made a reality. With the mission of photographing the majority of the Earth every day, Planet Labs created small satellites, individually referred to as doves, to capture ground imagery for use in humanitarian, environmental, and commercial applications. With the 2005 NASA Authorization Act designating the U.S. segment of the station as a national laboratory, the space station drives growth of a robust commercial marketplace in space through endeavors like Planet Labs. The Earth imaging mission of Planet Labs' Dove satellites takes another leap toward creating benefits on Earth, resulting from innovation in space.
What happens if you wake up in the morning and you understand the state of the world as it is right now?
What could that data enable? How could people make smarter decisions? How could, for example, a farmer get better yield on his or her crops? How could somebody help disaster response? How can we use satellites to help humanity? That, in many ways, was the underlying thesis of doing Planet Labs, was to get data into the hands of people that could enable us to make smarter responses to that.
Planet Labs set out with the mission to photograph the entire Earth every day. And they thought, how are we going to do this? They said, let's build our own satellite.
Commercial imaging satellites, they're very large. They are very expensive. We took a different approach.
By making them really small, we can launch lots of them, and by launching lots of them, we can cover this, to get to this mission of imaging the whole Earth every day.
If we can do that, then we can literally change the way that we see the world.
And they called it the Dove. It's about the size of a loaf of bread.
Our doves are basically mainly a big camera with a telescope looking down to take pictures of the Earth. We initially developed the first Dove satellite in our garage. So we kept on iterating the Dove design, we made it better and better, and eventually we put our first one into space. We had no idea what the quality would be like.
I mean, we didn't know if it was going to work.
But we got an image down and it was so beautiful that we knew at that point we could make this technology work.
Wow, we can really do this, and we can achieve this mission, which is something that is really needed for us to understand global change.
So we had done a couple of demonstration satellites, but the next steps we wanted to do was to scale it up, to test the first fleets of satellites.
But what made that possible was actually access to space.
So here's the problem, that in order to take pictures of the entire Earth every day, you're going to need more than 1 or 2 satellites. You're going to need a whole lot of satellites, and you're going to need to be able to deploy them really fast. And really, there's only one obvious choice on how to deploy that, and that's the International Space Station.
There was no other platform in the world in order to get access to space of that fashion in that time period than the International Space Station.
NanoRacks is our key partner with NASA.
At NanoRacks, we understood Planet Labs' vision, and we knew that we could help. We worked together to figure out what was going to be the best way to get as many satellites as possible, and we basically developed a new platform. It goes out of the GIM airlock, it's picked up by a robotic arm, pointed out into space, and it fires these little satellites off of the space station.
They were able to secure 28 of our satellites to be launched from the International Space Station, and that was known as Flock 1, our first constellation.
This opened up the whole world to satellite developers, people that could put things into orbit fast.
We now deploy these on a regular basis from the International Space Station. And now today, we're able to operate the largest fleet of Earth imaging satellites in human history.
And none of that would have been possible without the International Space Station.
The International Space Station does enable young, small companies like ourselves to get going in space.
The ISS provides a lot of opportunities for commercial companies to test and find where the market in space is going to be.
And so what we're seeing today is a proliferation of new ideas and new concepts. It's almost like it's a renaissance of what's happening in space. Buckle up and strap down, because this is going to be a rocket for all of us in the global community to be part of.
I used to think when I was growing up in Florida, lots of thunderstorms in Florida, you know, that here's this storm over top of me and it's just this individual little thing that just is about a storm over Florida. And in fact, now after looking at the Earth from space, I see that that little storm in Florida is connected to Africa and Europe and all across the planet. And one of the most impressive things to see is how the Earth presents itself as alive when you're watching these storms at night just trickle across the whole surface of the planet like its own nervous system. And the emotions of the Earth, you know, seeing storms that are developing and the way you know from having that experience on Earth how it's probably impacting the people and the places down there. It's like, oh, is it upset and mad today versus the sunshine over some other part of the planet? And really, really, really gets you looking at it in a different way, an appreciative and respectful way. When you're crossing the deserts in Africa and the way the dunes form, and they almost look like little, you know, birds have run across the sand. And then this contrast you'll get from kind of the pinks and oranges and whites to these dark grays and almost deep blues and of rocks and everything that are intersecting with it. And the Bahamas and the northern coast of Venezuela, which quite honestly is, I think, the most beautiful place on our planet. It is just incredible. Yeah.
Well, so far we've learned about using the ISS as a platform for iServe, which captures imagery of the Earth to provide disaster assistance, and deploying small satellites called doves. We expect good things to come from both of these experiments and look forward to their robust potential. NASA has selected proposals for 2 new future instruments, Getty and EcoStress. These sensors on the ISS will give scientists new ways to observe how forests and ecosystems are affected by climate change. Our next piece is about a recently completed mission of an Earth-observing instrument on the ISS called HYCO. Its name stands for Hyperspectral Imager for the Coastal Ocean. Check it out.
Carroll Township's a very rural area in northern Ohio, right on Lake Erie. Lake Erie has always been very important to Carroll Township and its residents. We use it for drinking water, we treat it, and it's really our livelihood.
In Lake Erie, for what unknown reason, suddenly the toxin level spiked, and that got through the treatment system.
It was indicated to me that it is pretty dangerous.
Cyanotoxins can cause skin rashes,
headaches,
nausea,
vomiting, stomach problems,
nervous system problems,
liver damage,
to death.
We sampled and we had about 2.5 times the limit from the World Health Organization. The second sample was approximately 3.5 times. Our plant wasn't set up to handle what was coming in from Lake Erie. One of my biggest worries was actually hurting someone or even worse. So we shut it off right away, shut everything off. We had a very close call that day. The last thing you want to do is produce an unsafe water and allow your people to drink it. What we need is a better way to track and predict these cyanobacteria entries from our source water so that we can make sure that this never happens again.
A lot of the times we'll find out after the fact that there's a problem with cyanobacteria in the water because the bloom's already occurred. We either get results of sick animals or sick people. We need a paradigm shift. We need to go from being constantly reactive to these blooms to having a capability that allows us to become proactive. And the U.S. Environmental Protection Agency has been very encouraging of allowing for some high-risk, high-reward projects. And that allowed us to think outside the box, way outside the box. We've been fortunate enough to make use of a sensor on the International Space Station called HYCO, which stands for the Hyperspectral Imager for the Coastal Ocean.
HYCO consists of 2 instruments. One is a camera, And the second instrument is a spectrophotometer, which actually gives us the spectrum of light leaving that water.
The camera on a cell phone, for example, contains about 3 bands of data in a red channel, a green channel, and a blue channel.
HICO gathers light from the red, orange, yellow, green, blue, indigo, and violet parts of the spectrum. So using this technology, we're able to now detect those water quality parameters such as water clarity, what the phytoplankton concentration is in your water, how much light is being absorbed in your water, as well as what's the distribution of cyanobacteria in those waters, and does that concentration pose a health hazard?
So what this means is instead of waiting for someone to report that there's a problem with cyanobacteria bloom, we can monitor these water bodies from space
and get information that we can rapidly get out to the water quality managers through a smartphone application that we've developed.
So the app allows you to drop a pinpoint, and that pin can be placed in an area where a drinking water treatment plant may have an intake, and see what the current water quality conditions were. Each user gets that information near real time, so they can make judgment calls on whether they have to respond or take action.
Having the HICO on the International Space Station has been the ideal test bed for our research.
This is an amazing partnership. The Naval Research Laboratory had HICO on NASA's International Space Station. As HICO acquired a scene, it was transferred to the Naval Research Laboratory. And then the Environmental Protection Agency was able to do the analysis and the validation to send this information out through a prototype mobile application. Yes, this technology will reduce costs and provide near real-time information. But the big goal here is protecting humans. And if we can reduce exposures both to humans and even animals, then we've achieved our goal.
Our International Space Station is an unprecedented research platform in space, allowing researchers and scientists to conduct experiments that can't be done anywhere else. Utilizing the ISS as a ready-built platform for studying the Earth is well underway. So far, we've learned about iServe, Planet Lab's Dove satellites, and HICO. 2 more experiments, or payloads in NASA speak, are on schedule to get to the ISS later this year. There's SAGE 3 and Lightning Imaging Sensor. SAGE 3 will measure ozone and other gases in the upper atmosphere to help scientists assess the ozone layer and how it's recovering. And that Lightning Imaging Sensor will monitor global lightning for Earth science studies and support operational weather forecasting and warning. Looks like utilizing the ISS to further benefit all of humankind? It's right on track. Thanks for joining us on Station Life at our behind-the-scenes look at using the International Space Station as a platform for studying the Earth. And be sure to follow us on Facebook and Twitter for the latest research news. And don't forget to download our straight-up gangsta app on your mobile device. It's totally legit. Until next time, we're working off the Earth for the Earth.
Welcome to NASA Edge, an inside and outside look at all things NASA. On today's segment, we're going to give you an update on the magnetospheric multi-scale mission with senior project scientist Tom Moore at NASA Goddard Space Flight Center. Let's see what NASA scientists have learned about magnetic reconnection. So Tom, I understand that you've been getting some great data from the MMS spacecraft. What have you discovered about the magnetosphere?
Yeah, the mission's been working like clockwork since it was kicked off off the launch booster. We have been seeing we're getting into all the places that we'd hoped to see and measuring all the things we'd hoped to measure. The amount of science productivity flowing out of the team is just difficult to keep up with. One of the things we caught is electrons doing their dance in space, or doing the weird things they do that actually enable reconnection to occur. And this happens on the very tiniest scales, just a few kilometers distance. And normally those scales have been invisible to all previous missions, but with MMS we flew in there and we could see a signature in the electrons of trajectories that some people thought those particles were executing. And it shows you how the electrons go from being sort of immune to energy dissipation to becoming an electrical current like we think of it that can dissipate power, and they can be accelerated by the electric field, the magnetic field in that case, absorb energy and take energy out of the plasmas that are driving the reconnection. And that is the key. That process makes reconnection possible, and it probably also sort of limits and controls how fast reconnection can go.
Well, how often so far have you seen reconnection with the MMS?
Well, we see it all the time. I mean, almost every time we pass through the magnetopause separating the magnetosphere from the solar wind, we see, you might call it the features of reconnection. Sometimes the place where the X line is, where the fields are crossing, that can be fairly distant from us. And we're seeing an exhaust flow. It's kind of like a big pump in the sky when it gets going. It sucks material in and spews it out continuously. So we often see the jets of flow exhausted from reconnection that's going on. But the key, right, for this electron stuff I'm talking about is that you have to fly right through the X line, and it's very small, very localized, so you have to get lucky. So far we've hit it maybe a dozen or two times on the day side of the magnetosphere. We also see lots of other stuff. In addition to this core process of reconnection, we see what you might call dynamics, the solar wind taking a bite out of the magnetosphere, if you will, kind of stripping off a layer, wrapping it up into a rope, and flinging it off the magnetosphere. It's kind of like, we call those a flux transfer event, but it's basically taking a bite out of the magnetosphere, ripping it away and carrying it away downstream.
Has nothing to do with the flux capacitor.
As far as I know. Okay. I've been trying to connect those two.
Based on the MMS mission and what you've learned to date and what you hopefully will learn in the next couple of years, what are some other aspects of the magnetosphere that you'd like to maybe study now that you've kind of you've caught reconnection, you've seen it, you've seen the data? What would be the next step?
Well, there's a couple of topics that bubble up all the time. They're particle acceleration and turbulence. And so, especially as MMS completes the tail side phase that it's entering now, it'll go back to the day side, but at twice the radius, twice the distance out. So it'll be well out in the solar wind. So we would like to study solar wind particle acceleration and turbulence. There's not much reconnection out there. Sometimes you'll get different pieces of the solar wind that are reconnecting with each other. The fields have gotten twisted or something and they're relaxing. So you get turbulent features and you get particle acceleration events going on, some of them traceable way back to the sun, but some occurring locally in space. And that's really the next thing we're headed for on the day side.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.